Hello. Good afternoon. How's everybody?
Good. Confused by the weather.
What's confusing? Well, it started a little rainy, right?
Well, yeah, there was a thunderstorm and then it's like 30 degrees. So I don't know.
Right. So you know what they say about the weather in Texas. If it's raining,
My
just
first
wait
time.
for 5 minutes. It's going to change. So thunderstorms, they come and go through. I actually noticed first time around here, like over time, you kind of get used to like constantly sunny, and even if there's a thunderstorm, it's gonna like kind of blow through and like it's gonna go back to its sunny equilibrium. And then there was one time, like it was possibly even last year, where it was like kind of like gloomy for 3 days in a row. And at the end of the third day, I was like starting to feel slightly depressed. And I'm like, look at this, like it cannot be. We're not used to 3 days of any kind of cloudy weather here. We need our sunshine intake. So once you get used to that, it's kind of hard to go to different. But anyway, but this is the season when we're supposed to get rain. Rarely it's going to last for days, but we are supposed to get thunderstorms April and May because that's the rain intake that Texas gets, and then it warms up. Anyway, well then, let's get back to our class. I need to share the screen. Share the screen. So today we're gonna briefly wrap up surfaces and basically what ends up being visualization because they're used for visualization the most. I have quite a bit in that lecture 6. I have quite a bit of information on measuring areas and curvatures from the data, especially when it has multi-phase data in from the data, whether it's experimental data or simulations. However, I'm not going to spend time on it. I realize we have basically today and 3 lectures left, and I would like to move on to the one thing of how two advanced topics, and if and one of them is the estimation of permeability using direct simulation methods and not just the networks, and then a level set method for 2-phase flow displacement, where we will go back, touch to surfaces and curvatures once again. But I'd like to have time for those, and then we can see that a third lecture I might actually do sort of like some of the most recent work on machine learning that is done in my group. So sort of like 3 more advanced topics remain. I haven't published the homework. I will publish it today. I'm actually trying to push through a data set in DigitalRocks portal. By push through, I mean publish. They get reviewed and published just like anything else. That I actually think is very exciting, and it's going to be part of your homework for visualization in any event. So I will actually just quickly show it right now. So in addition to you can already start working on those. I pointed those out during the slides, but there will be network exercise on pore throat networks. And you can choose whether you want to do 2D or 3D. And then after that, you will do exercise 3 network models. That's from slides by using that MATLAB code. And then there will be a visualization exercise, and I'll actually ask you to plot, well, you will be able to choose, but let me show you the data I'd like you to. Actually, I'm logged into the other one, so maybe it's better to go where I'm logged in. Chrome, this is Chrome. All right. So just to actually show, speaking of visualization of surfaces, if you kind of walk through these projects, even if you're walking through the just project pictures that are chosen as the cover photos for projects, you will see surfaces. So as I walk you through here, these two, this micro-CT, it's typically surfaces that are visualized. So these two are visualizing interface between pore and grain. This is Javier Santos' pictures. It's visualizing, actually, this is a two-dimensional, two-phase lattice Boltzmann simulation. So you're seeing interface of a fluid in a fracture. So this is advanced use of ParaView, by the way, where you have a slice that outlines where the fracture is in sort of one cross section, and you have a three-dimensional, so the interface between two fluids, it's a rough fracture, is actually shown as orange in this particular case. This is interface, so this is one of the most common covers in a lot of images show interfaces. This is experimental work, and it's showing interface of trapped phase, non-wetting phase in without any other surfaces. And typically when it shows different colors, it's typically different disconnected components, different blobs of fluid. So this is another one where you actually see a blob inside sort of a see-through surface, which is the type of visualization we did as practice in last class. So these are cross sections, obviously. Cross section. This is a visualization of a streamline. For this, you need to actually flow or velocity field computed in order to visualize it. And it's inside pore grain surfaces shown with very low opacity, so it's see-through. That's that opacity part that we were playing with in ParaView visualization. This is a cross section. This is three-dimensional. This is actually analytical data. So these spheres are actually really pretty. This is Abhishek. A lot of you probably know Abhishek. He's about to graduate from our department. So this is spheres, and these are actually analytically described. So you can basically plot them as very well-resolved spheres. This is a granular medium, so you can see the biofilm as well as surface of a biofilm, as well as the surface of the grains in the porous medium itself. So you can see, like, I can keep walking through. So basically these interfaces, people either choose to show a cross section or interfaces, especially if it's three-dimensional. Okay, so again, these are again streamlines, and you can keep going and you will see a lot of interface visualization right there. Here's some fractures. Again, this is from some of you might know Jeffrey. So this is showing fractured surfaces within sort of a volume rendering of the grayscale image. Okay, so you can see different combinations. These are individual vugs in a dolomite. There's some gold on DigitalRocks portal as well. You can see gold grains scanned within section and so forth. So you can see that, like, interfaces in terms of visualizations are really important. Okay. Oh, I did promise that I'm gonna show you what are you gonna get as a homework once I publish it right after this class. What? Doesn't want to click. Okay. All right. So one of these, so there's a number of sets. So I would like you to actually practice some visualization of vector fields, and you will actually get that as a, so where's that one? See, surfaces are everywhere. I'm just going to type it in. I am right now the only one able to, oh, no, 273. No. No, that's not it either. Well, I have it in that home, or is it 170? This is me guessing which project number it is. Yes, that's the one. So there is actually a PIV measurement, a particle velocimetry measurement of velocity field. So this is experimental measurement of velocity, which is pretty dang rare. And this is the first time I've seen such data shared on DigitalRocks portal. So I'm actually really excited about it. And what there are fields. So let me see. There's basically X, Y, Z field. So you can see just basically velocity, X, Y, and Z components. Okay? So you can integrate those to actually get the permeability from real experimental data for this sphere pack. So one thing that I'm going to throw out there immediately, you will be asked to either, well, these are pretty large. There's quite a number of slices in Z, and then there's X and Y. So in case it's too much for your computer, just resize to a manageable size. Take a 300 cube or something subset of it that you can work with and effectively visualize. Okay. So again, this is an exciting data set because and it's again, velocities are expressed in meter per second, and you can try to get the average velocity, and I'll ask you to calculate permeability in X, Y, and Z and see whether it's similar. Okay. So that's going to be a little visualization and manipulation of the data exercise. All right. So that's going to be in addition to the two things that I mentioned already. And that's going to wrap up the homeworks. So that's going to be due next week. And that's going to be wrap up the official homeworks for the class. I want you to work on the project. And then project, we can decide on the, so, well, I need feedback from you in terms of how advanced are you in wrapping up your project. I'm thinking as long as you submit a PDF describing it by the end of the finals, that'd be great. But I will also ask you to meet with me to present on it. Okay, and everybody else will be invited to view those presentations, so we can actually kind of all enjoy what everybody learned in the class for their own project. Okay. So back to surfaces, we've seen a number of ways to visualize surfaces. I have worked through example of that oil blob and visualizing oil blob in a sample of limestone. That's example 3 in the slides I'm going to post for you. But there are 2 more examples in there should you wish to practice a little more with ImageJ. So there is both volume viewer and BoneJ isosurface plugin on sphere pack datasets if you want to practice a little on your own. This is the sphere packing that we've analyzed a lot for all kinds of things in this course. And there's also a ParaView example of visualizing a surface of that sandstone. That's again the sandstone that we know really well in this course. So if you want an alternative example, you can take a look. One more comment that I'd like to make about the surfaces and that I made that comment already, but I want to reiterate. So when do surfaces look smooth? When do they look binarized? It depends on the underlying data. You can kind of filter the smoothness of the binarized data interfaces, but in that case, you might be losing some information. So here's an example of smooth rendering of analytical data. So here the described distance function was analytically calculated. So that can basically move those interfaces in Marching Cube algorithm to look really smooth. So this is how it looks like. If you have a digitized version of it, no matter what, near where you have interfaces touching, you're gonna still see something like this, because there are some topological issues near point contacts. There's multiple ways to interpret the same point contact when in a digitized world. So this will result in something that looks like this. Okay, unless it's smoothed in some way. So don't be terribly disturbed. This is, again, just a little problem. And you can see how kind of surfaces have like little jagged edges near those contacts. It's just a problem of resolving a point contact. Or if you have binarized, so this is even when you have smooth data, that's finite resolution near a point contact. And then we have a staircase effect in case of pure binary surfaces, because if you have zeros and ones or just two values, that's going to result in triangles that are essentially either aligned with the grid or at 45 degrees to it. And that's what you see in these images. This unfortunately is not online anymore because my former ISIS, so I did not embed, unfortunately, the video here. These are some visualization. This is visualization actually from my PhD work. I was analyzing experimental data and at imbibition and so residual saturations both during drainage and imbibition. So what was interested is that if you take this was a Berea sandstone example, and there was first saturated with water, and then there was drainage, and at the end of the drainage there was a water residual, and you could see actually here the grain interfaces were not shown, but this was really hanging out close to the grains as a bedding fluid would. And also you could see that this was the largest blob of water inside of that volume. And then after that there was imbibition, and then there was oil residual, and oil was hanging out mostly in the pores, in the middle of the pore spaces. It was interesting to me that the largest oil blob and largest water blob inside the same medium at two different instances were at completely disjoint locations. So there was a portion that was kind of trapping a lot of oil, and there was a portion that was trapping a lot of water, probably because of the heterogeneity of the pore spaces and their sizes. This is actually also on I use this image a lot on DigitalRocks portal. This is from a level set simulation that I'm gonna have chat about as an advanced topic next week. So this, you see the residual non-wetting phase inside the pore space in the very similar, actually, piece of Berea sandstone. It's just that because of the finite size that was used in the simulation, you will not see the blobs of the same sizes as they were subsampled from the experiment. So this, yours truly was, right now it's very common to visualize things. I was actually in 2004 or so one of the first people to actually plot these, and I actually designed my own little surface visualizer. There was no part of you at the time. Yeah. Now you also want to quantify these areas, so you can sum up the sum of the triangles. And I'm just going to point out that the rest of these slides have some work and research done on both verifying how these interfaces are computed and what is the best practice. One common problem is when I have multiple phases in an image. So here is one example. I'm going to actually fast forward to a problem. And this I need to actually add a reference. This is from one of the papers I published in 2006. So when you have three different phases, so this is an example in 2D, the problem when you do interfaces and is that you can do interfaces between two things. Okay, technically you don't do it in between 3. And if you do have multiple phases, then you have to repeat this interface and basically overlap some of them. So what happens here is actually a little interesting because of the digitization, and I just want to point that out. So if you have, let's say that this is solid, these pixels are solid. If you put interface between solid and everything else, you will get this straight line. Okay? And then if you have, let's say that this is fluid 1 and fluid 2 in this sort of mock example, then if you put an interface around fluid 1, you will get something like this. This is a contour around it. Okay? And then if you put the interface around this, you will get something like that. So technically what should be a point in the middle, which is a triple contact of these 3, you cannot get by intersecting these interfaces, because there's actually an empty triangle in between, in the middle. And in 3D, this thing has volume. So actually get a triple point at the intersection of these 3 phases as computational geometry exercise where you actually have to kind of extrapolate this interface, or like go and figure out how to split this interface into 2 pieces that actually properly overlap. So that's something to think about. So what's done in terms of actually estimating the area, we are often interested in the area, which is here, which is in between two phases. So that's interface, oil-water interface area. Okay. What's often done is this following formula. You compute all of these interfaces separately. Water, area around water, area, in this case, air and solid. So if I took this area plus this area, okay, then I'm going to basically double up this area and I'm going to get 1 solid. So if I subtract solid and divide by 2, I will get an estimate of this interface area. So if I add up individually computed this area plus this area, I have doubled up the interfacial area between these 2 fluids, and then I just have to subtract the solid area to get it. And of course, I'm having a little bit of error around here because they don't completely match, but that error is relatively small. So what's widely accepted to calculate the interfacial area is taking that between 2 fluids, in this case, I label them air and water, you get 1/2 of area around water, area around air, minus area around solid. That's for 3 phases in the image. Okay. And then there are some papers on verification of these, using different algorithms for this area, verification of the accuracy. Okay. And I'm not going to go, you could also go into relate, these areas are relevant in thermodynamics. So there's work in attempting to add that, and that's a little beyond this course. But basically, there's a way to verify theoretical approaches from early 90s using data computed from experiments or simulations. One more thing that I'd like to comment on is curvatures. So again, just like you can calculate areas, you could calculate curvature of the interface. And I'm gonna point that out a little more during our level set discussion next week. Okay, so that finishes our lecture on surfaces. Are there any questions or concerns before I move on to the next lecture? Everybody awake, around? Is your coffee strong, afternoon coffee, or whatever drink you need to stay awake?
How can, in the slide where we were seeing the 3 interfaces, how the intersection between the 3 interfaces can have a volume if that volume for it's less
because
than
it's not intersection. The thing is that the way surfaces are done in this digitized world, they're kind of pulling away from each other. And that's because I don't have a true point. So my digitized, that is similar to the topological problems in the digitized world. Each voxel or numerical cell has a volume. And there's that, I'm expecting a point contact, which is one vertex of that small volume, which is my smallest unit. But the way we are creating interfaces, I mean, it's artificial result of, it's not even that it has volume, they're just pulling away from each other, because this here is the interface between this phase and the rest based on the marching cubes algorithm, right? Marching cubes in this, all I know is that I have to go through this vertex and this vertex, right? And in between this straight line is an approximation. It's a straight line approximation. I don't know what interface here is. I don't have enough resolution to know, right? So technically, this line, this green line, should be some sort of curved surface, right? And this line should be some sort of curved surface that meets the other one. But computationally, I can't get it because, again, I just don't have sub-resolution information. So formally, I don't even have a point where they meet. I have to somehow extrapolate a point where these two meet. Does that make sense? So it's just the result of this odd space of digitized topology where what my points are actually are voxels that have volume.
Okay.
So it's artifact. This artifact is sub-resolution, right? And therefore it's within of the accuracy of what an image can tell you. Okay. So you have to kind of massage it to get the result. And I'm gonna show you how that looks like in 3D when I try to massage it and get, and to this date, I'm the only one when visualizing these. I'm splitting my interfaces into two because nobody really wants to do that exercise because it's not very accurate near this. It takes some extrapolation. Yeah. All right. So we are now going to move on to our next advanced topic, and we're going to actually have a fun demo. Lecture notes. So I'm going to introduce you to this date, the most common, what I call direct simulation method. That's the method that uses data such as this image data, wherever it is that I have pore spaces and solid spaces, and tries to compute a velocity field basically it computes a velocity field for every point inside of that data set. And it's working with images directly. A lot of times simulations like that are called direct simulations, as opposed to networks, where networks basically simplify my geometry, and then I have some sort of digested form of geometry, and therefore it's semi-upscaled, it's not direct. Okay. Now, there are some, Lattice Boltzmann is so common, and not just in porous media, that there is a whole lot of, a number of books out there. There is one classical one from 2001, that is the Lattice Boltzmann equation for fluid dynamics and beyond by Suki. And then there is a later one that is an introduction, sort of a version of the Lattice Boltzmann modeling book for geoscientists and engineers. So it's working a lot with porous media. Again, Lattice Boltzmann is a generalized equation, so it's for any fluid dynamics problem, really. However, not everybody is working in porous media. The reason why it took off as one of the favorite methods in porous media is that it's able to deal with these images directly without simplifying them. And it has normally so many interfaces that we have in porous media will cause trouble in discretization of the porous medium and will cause convergence issues in more classical finite element methods. Okay, so in that sense, it's going to be difficult to work with porous materials using finite element methods, and Lattice Boltzmann got popular because it's relatively easy to implement. And let me give you an example of relatively easy. I'm going to show you a two-dimensional version of the method that got coded up by my student. Some of you might know him. He graduated last semester, Rui Zhu. And it's just like a quick MATLAB. You will see that script is not that long. It's something that you can sit down and implement in a day or two. The problematic part comes running this example on a larger medium, which yours and my computer is not enough to do. Okay? So it's parallelizing. But even in parallelization, the method does relatively local computation, which makes it relatively easy to parallelize compared to other methods. Okay. Even when it comes down to 3D, I have personally, I did not do parallelized version for my PhD back in 2005, but I really literally sat down, and from day one to, it took me 6 months to basically code up the method in 3D, implemented in the particular example that I wanted, a single phase Lattice Boltzmann. Implemented in a particular example, I was calculating individual throats in a Berea sandstone, finding their geometry in so somewhat simple but still porous media geometries that I could actually process on my machine. And even that machine from 2005, I was able to get results within 6 months or so and have a paper about it. So in that sense, that was near the end of my PhD. So I was a little better at coding than I was at the beginning of my PhD, but it shows you that it's possible to basically get going and do something in a relatively small amount of time. Okay, so that's what makes Lattice Boltzmann methods popular. And on multi-phase flow, there's recently a book on multi-phase Lattice Boltzmann methods. I think this is it's relatively recent, but you can find it. Our library has it. So this would be some of the suggested books. There's also various PhDs out there. Whoever has a PhD that is using Lattice Boltzmann method has a chapter summarizing it. So this is one example from one of the doctoral theses at UT. Okay. Now here's the basics. So if I have a porous medium, okay, technically I'm looking at the box inside a voxel. And if I think about fluid in that box, let's say that I have gas, I have gas molecules whizzing around. And they're whizzing in all kinds of velocity directions. All of them have their little randomized velocities within, and they're colliding, and those collisions are basically what's at the core of the momentum transfer and ultimately resistance to flow that we measure using viscosity. Now, what Lattice Boltzmann method does, it says, okay, I can't have velocities in all directions, but I'm going to put them on a grid, and I'm going to allow every discretization of the velocities that has a finite number of them. So in 3D, so here you're seeing an example here of 19 velocities that are allowed. This is that 18 from 18 connectivity, if you remember. So this is at the center of a voxel. I take 18 instead of 26, and plus the velocity of staying in place, which is 0, that gives you 19. So this lattice or discretization is called D3Q19. So Lattice Boltzmann methods will typically have this labeled D3Q19, D2Q9, D3Q27 that basically tell you how many velocities am I using as a subset of possible velocities. And so lattice is translated, so at every point, what I will have is I will have a distribution of, or something that tells me how many or what fraction of particles assumed fraction of molecules in this box is moving in which of these directions. So if I have 19 directions, I will have 19 numbers describing the fractions of the particles moving in allowed velocities. Okay, so I can do that voxel by voxel, even if it's tedious to collect all of those voxel by voxel. It's done in a straightforward manner, right? I just take every voxel where I have pore space, boom, I represent it with 19 velocities or 19 distributions that point how the fluid is moving. Now, in this particular image, white stuff represent pore space. This green, you see volume rendering. So this green stuff represents solids. I will also have to apply boundary conditions, and those are in these like yellow voxels are those that are bounding. So those are the solid voxels that are bounding the pore space, and they're important for implementation of the boundary conditions. Now, technically, idea of this lattice Boltzmann comes from something that was originally known as lattice gas automata, that were literally thinking of bouncing molecules around. But then it realized, okay, if I'm bouncing molecules around, I'm gonna go nowhere because I cannot represent as many molecules as I realistically have. I mean, just one mole has 6.2 times 10 to the 23 molecules, so I'm not gonna make it computationally tractable, which is this idea of fractions of molecules that came in. So it's called mesoscopic model. It's somewhere in between looking at individual molecules and averaging them completely by representing things with viscosity. Viscosity is basically average property of the fluid behavior at any point, which takes averaging of the entire phase into account. Okay, and it's gas kinetic theory that does that. So if I wanted to prepare my velocity for this type of simulation in image J, I would take an segmented image. So I need a segmented image. One thing that I would also do is I would process it to identify only a main connected component or things that are connecting. If I'm about to apply pressure gradient from one side to the other, I better have connected stuff, because disconnected stuff is going to cause convergence trouble. Okay? It's not that you have to do it. Sometimes your simulation can still work it through, but it's a problem if I have a disconnected piece of volume and I'm pressurizing things in my numerical method. It's going to blow up, or it has a potential of blowing up. So this is my pore space, this is my grain space, so I can easily identify where it is that I have these fluid nodes and where it is that I have solid nodes. Now, how would you identify this yellow layer of what we call bounce back nodes? Those are the ones that I'm going to apply boundary condition. What would you do in image J? You know by now everything you need to know. So I need somehow to create a procedure that will tell me, okay, this is where my bounce back or boundary nodes are. Any ideas?
Maybe eroding one time and then subtracting the images.
Correct. So basically, if you erode and then subtract, you will get basically these bounding nodes identified. Okay, so that's one way. So that would quickly give you, this procedure would quickly give you that result in image J. Okay, now let's go back to the basics, and I'm now just going to describe this a little further, what I was talking about in 2D. So this is what the method does. So this is in 2D, 1 pixel and its center. And essentially, I have 9 possible velocities. That's basically 8 possible neighbors to this pixel. So I'm going towards those neighbors, essentially. And I have the possibility of staying in place. So 8 plus 1 is 9. So this is so-called D2Q9 lattice. Now, I'm talking about distributions. So I'm saying that this there's different distributions, okay, that take, these velocities are typically labeled as E0 through E8 in this particular case. So my rho or density is going to be sum of all of normalized density, of course. It's going to be sum of all of these distributions. So portion goes in this way, this. So it's really like a mass fraction, really. So it's some sort of a normalized version of density. And my velocity, or rather my momentum, is sum of all of these fractions going in different directions times individual vectors. So that gives me momentum, rho v, and I got or rho u, and I got have to divide it by rho, which is this sum, to get what velocity is at that spot. So what we're going to calculate or discretize in this world is Lattice Boltzmann equation describes how these FIs, these distributions, these portions of fluid moving in different directions, how they change as they're trying to get to an equilibrium. Okay? And basically, I will, at every point, I can evaluate what my density is. This is assumed to be ideal gas, so I can also, by knowing density, I can also relate it to pressure. And I have a velocity, so I have a velocity field basically at every point. I can evaluate velocity by doing this. As long as I know FIs, these EIs are static, and rho, of course, I can compute. Okay, cool. So how does this equation, actually, Lattice-Boltzmann equation, looks like? I have to know what is the equilibrium, and while equilibrium is somewhat of a moving target based on the current distribution of velocities, I'm going to always try to kind of equilibrate and get to that equilibrium at certain rate. So the simplest equation, which is not always the one that works the best, but it's always the simplest to explain and understand, is saying, okay, at my next step, I'm going to basically collide all of these portions of fluid moving in different directions. And as they collide for something coming from the other direction, they're going to exchange momentum. And based on that, some of them will again get into different directions. Okay? And I can move only, in this case, in 9 possible directions. Okay? So basically what streaming does, it calculates based on the current rho and u, or FIs, if you will. Okay? I will see how far I am from this presumed equilibrium. Okay? And I'm going to calculate this portion. And then I'm just going to, at the next step, say, okay, these are my distributions at the next step, delta t. Okay? And I calculate them along these directions, directional vectors EI. And that's pretty much it. So if I give you this formula, all of you can basically go calculate these things. You have to, of course, know what that delta T is. And what is this? This is something that is equivalent of the resistance, or 1 over tau, or viscosity. Right? So you need to know how, so basically I'm related to viscosity and how slowly I'm getting to that equilibrium, or how fast, however you want to look at it. Okay? And then this is the single relaxation time. Now, there are some other, so I have a single version of tau that works for everything, which is not always the most stable, but it's the simplest to implement. I could make that a little more complicated and have multiple relaxation times that are actually part of a matrix. And then instead of just dividing by tau, I would actually have here a matrix multiplication. That's really what it is. And these are typically given. And then the second portion that you're missing, so I've gave you, there's a formula here for this equilibrium distribution. There's a whole bunch of physicists that are working on this, and they're basically calculating what these equilibrium distributions should be based on kinetic theory of gases, which this is based on, as well as, well, what should it be so that actually when I actually collide over time and do these steps, I'm going to recover Navier-Stokes equation to a reasonable degree. And that has been proven that given certain assumption, you actually get Navier-Stokes equation as a result. Okay? And the only problem in the whole thing is that, okay, what do I do with the boundaries? What do I do next to a solid wall? Okay? And the second problem is how long does it take to actually equilibrate? So I am stopping when I actually get to equilibrium, which means that these FIs are not changing much. So just like any other numerical method, I need to evaluate, okay, did I reach that point where I'm not changing much? And what does it mean not to change much? What is much, right? So that is basically your, in essence of every numerical method is a stopping criterion when it is that you're happy with the result, and that can vary or it doesn't have to happen. Okay. So this is the simplest of the boundary conditions. Again, it's not the best, but it's the simplest to implement, which is also what makes this, this method really popular for porous media. So basically what happens near the wall is like I'm assuming, so these are my solid pixels, and these are fluid voxels. So presumably my fluid would stream into that wall, except that it's a wall, so it shouldn't. So then basically I pretty much the way it's streamed, I reflect it back into my pores, into my fluid nodes. And that is it. So basically while going here, whoops. So I wanted to go, whoa, I wanted to go into the wall. Well, but it's a wall, so I'm gonna just bounce them back and stream them back into the fluid. And you can describe this essentially, so for this velocity that goes into it, I have the velocity that is pointing in the other direction, and I know which one, so you can basically write down what should happen and which one should stream back, okay? All right, so let's visualize this. There's the LBM demo in MATLAB. It's available online. It's in the data. So let me know. I have posted it in data. So there was that data that I shared with you, the entire folder. And that folder now has this LBM demo that, again, I downloaded from online. And there's also an example code by Reju, sorry. And then, so if you want to look at it yourself, you can. Let me see, I need to open MATLAB and point my. Here's my desktop. There it is. You can see that I'm old school. I still navigate to something. Where's my box? Maybe it's here. Okay. Okay. So you can just do the view and run it. Is it running? Okay, let's try this again. Did it open two for me now? Not showing. I haven't had a problem with this before. Did anybody get to it? Do you have trouble running?
Looks very fancy.
It is fancy. Why isn't it running or showing is a mystery to me. It's a fancy visualization. It's a great visualization, but it's basically showing what I was showing right now. It's pretty slow, but that's not the point of it. The point of it is to visualize. So can somebody share on video? Danny, do you have it running? Let me.
Yeah, sure, I can do that.
Yeah, I don't know why isn't it showing, but instead of me spending time figuring out why, let me get to my. Okay.
Let me just restart the thing.
Mm-hmm. No. New share. I want to stop sharing. Pause share. Stop share. And then I allow you to. So can you?
There we go. Is it working?
Yeah, I see something. Okay. So this is basically showing velocities. And so you start with basically zeros, the streaming procedure in all directions, and then they come back from the wall and they start adjusting velocities that would normally kind of bump into the wall. Those walls, which are obviously simplistic walls in this case, are starting to shape velocity to go through the porous medium. And we know, well, from basically fluid mechanics or transport class that you took, you know how walls affect a lot, because walls will ultimately result in a zero velocity at the wall if they're static. So they tend to shape, it's these boundary conditions on the walls tend to shape the velocity field in a big way. So as you keep going, this velocity field will adjust, and at some point it will kind of stop changing much, and that's the point when you say, okay, I achieved a steady state flow through this porous medium. It is fun times, but all it does is, again, it's just visualizing those velocities. Curvature function will do that. So when you calculate U's and so your velocities that have X and Y components, UX, UY, VX, VI, VY, however you call or refer to those, or U and V sometimes. So when you calculate them, you can visualize them with the function called Curvature. I'm going to ask you for your homework to do this, well, using ParaView. So basically, you need to place a little vector like this that is scaled to the velocity. It cannot be always properly scaled, but you can kind of roughly scale it. And the main problem visualization of these fields, this is a very simple pore space where I don't have that many pixels. So I can show a vector at every pixel. What visualization tools have to decide is to kind of do a sub-selection of the pixels where you're gonna actually put this little vector visualization or whatever you use as a visualization. And choosing that selection is not always simple, because otherwise it gets too busy, right? So good selection of good coverage is not always straightforward. And these you can put at the point, at any point that you have when you're visualizing a field. In this case, we chose there is this chosen little vector that is shown. What you put at that point can scale with whatever your field is. So if it's a pressure field, it could scale with the pressure value. If it's velocity field, where it should point in some sort of a direction. And what you actually put as a point at every point is called a little glyph. So a little object that is oriented and colored in some way that is reflective of the field you're trying to visualize. So that's a visualization problem. And again, you will be tasked in your homework to figure out how to do that in 3D. Okay, all right, so this keeps going. It's obviously a rather slow script. What I want you to now go and do is open the second demo, and I don't know how are my visualization working, but I'm gonna try. So I'm gonna stop. Apparently it's working. I don't know where is it sending. My MATLAB is sending these images somewhere, or it should be sending, and it's not showing up on the screen. Oh, now it's showing up. That's hilarious. Or at least the figure is showing up. Well, I'm not gonna debug that now. I haven't had trouble with this so far, but there's always a first time. Now, let me share. Screen share. What I want you to go now, and let's see how is this other one working. So also in data, there's LBM code by ratio. Okay. And there's a slice of sphere data, or that beads slice that we've worked with in a lot of exercises. So this code, again, this is for your own use. This was put together by Ray, and I want you to basically appreciate how relatively simple it is to write this code. So you set that relaxation time tau. We're going to have a gravity forcing here and density, and then you need to set the maximum number of iteration steps in case you're not converging. And then what is the precision, or what are you going to call steady state, and when your differences in distributions don't change much, what is that much? So that precision is 10 to the minus 5 here. And basically, you read the image. MATLAB has all kinds of image reading routine. This image is 0 and 255, so we're going to divide it by 255 and get zeros and ones. And then essentially define the geometry. So there's n, y, and x of data. And you will allocate memory for these fluid for distributions FIs. There's 9 of them at each point. You're gonna equilibrium first. This is that equilibrium F and so forth. Then you initialize it. Okay, so you initialize the field and define these lattice vectors that are pointing. Each of them have EX and EY component, and there is 9 of them, right? So this is just the definition of those vectors. And you're gonna set your velocities and your density rho, okay? And then you start the thing, and you will basically see the streaming and collision steps. You have to compute the equilibrium distribution using those defined velocities. Then there's a collision step and streaming step, okay? And that's pretty much the end of it. You just keep looping, and at the end, you visualize. So there's a visualization step. So let's see if this is working. Well, it's computing. There we go. And this is the profile of the speed, which is square root of ux squared plus uy squared. And this is obviously velocity filled in between those spheres. And velocity there is 0 because they're solids, so that works for visualization. Okay. And it's changing, this profile is changing as I'm still converging. Still working on it. Has everybody been able to run this? It's converged in 86 seconds. And you can also plot streamlines. You can see how to visualize streamlines in MATLAB. Streamlines is something that is visualized in ParaView in 3D as well. And that was actually one of those streamlines is what I showed at the very beginning as a cover picture of all of the projects. There's a project on DigitalRocks portal. These are the streamlines in 3D going through Benheimer sandstone. Okay. What is the second? And this is visualizing the velocity profile. So this is just a selection of points. So I'm not actually showing velocity vector at every point. That is, you will see there is a selection. Streamlines, where's the second velocity profile? So this is the select basically every 10th. So this is something that you can play with to show where to put them, where to put those little vectors. Okay. What I want you, well, let me just point out something in the slides. You need, for any realistic three-dimensional image, you need something more powerful and than MATLAB and do parallel simulation. There's lots of open source software at this point. There is 3 open source ones that I suggest, but they're not the only ones. There are more. There's OpenLB as well. Palabos is the one that has been worked for a lot of cases that I know in terms of just immediately compiling without a problem. My students have refused modifying Palabos. It's apparently a little harder to know what's behind, even though it is open source and you can modify it for your purpose. They have reported that that part takes a little bit too much software engineering to do. Then there's Taxila LBM. I know about it. There's a paper about it. We were not able, I tried once though, but I was not able to compile it on TAC, Texas Advanced Computing Center here. And then there is code by James McClure that does relative permeability color model, and it has also a lot of tools for segmentation and morphological analysis, and it has both MPI and GPU support. It's one of the most powerful in terms of scaling and ability to run on large images. However, again, it might, the more powerful the code, it's a little possibly harder to modify for your own use. So that's something to take into account. James McClure is a collaborator of mine. He's at Virginia Tech, and he's open to collaborations, so he will typically respond to inquiries if you would like to use that code. Now, there is, oh, wait. There's a Palabas version. What happened? I guess I modified the wrong lecture. So Javier Santos, not Javier in our class, has together with Abhishek Bihani came up with the sort of an interface on how to use Palabas for multi-phase, for two-phase simulation. So that is available on GitHub, and I apparently did not add it as I was. So this is basically a multi-phase interface to running Palabas. So he, Abhishek, and Chris Landry, who used to be research associate in my group, have put it together. Okay. So one more comment is if you want to determine permeability, you can find the average velocity just simply by averaging all of the, you don't have to just look at the X or Y or Z component or one slice of the data. You can actually just average all of the data, because technically if you have an equilibrated simulation, you should see the similar flux through every slice of the data that you see. And then you need to scale from lattice units to those. So note that lattice Boltzmann works in terms of simulation, it works in lattice units which are normalized. So they have to be scaled back to the realistic units. So I'd like you to basically run Reju's code, but what I want you to do is to find some other image, whatever slice of whatever it is that we worked with, and process it, one slice of data, save it as a, so you will see that that MATLAB code, all it takes is the same code. If I give it a TIFF image, so you can save in image J a TIFF image, okay? As long as you get that TIFF image and it has zeros and 255s, the rest of this code will work. So you basically, you can drop into the same folder TIFF image of something else that has been segmented and that actually you can move through. And I want you to run this code using that image. It should percolate. I can make some suggestions on DigitalRocks portal that shouldn't require too much modification. There's a case with micromodels. And if you take a slice of a sandstone from a three-dimensional data set, be careful to erode it. So a slice through this would work well. That's the slice that I actually like putting in my background. You just take just the pore space. You could take a slice through a fracture if you'd like. There's a micromodel project by Ashar Mehmani, who is our alumnus. This one. So you can maybe try to, I think those tips are posted. Let's see, Berea micromodel. That's a sample. Yeah, you could use something like this. There's Berea TIFF, and all of the micromodels here have TIFF versions. So there's regular or irregular, whatever you like. And see, or you can just process something yourself. So again, all we need is a TIFF of zeros and 255s, or if they're not zeros and 255s, you can just adjust that code. And I want you then to, actually let me I'll open a canvas, so I'm gonna collect those contributions from you. So I want a picture of the velocity distribution through whatever geometry you decided to use. You can also draw something yourself in your favorite paint stuff and just binarize it as an input. I'm gonna say due today at 11 p.m. There. All right. So you can finish this right now, and I can share the gallery of the results for fun on Monday. But I will see you on Monday. So let me know how your projects are going. And if you need any help from some of you I've heard from, but not from everyone. All right. I see you on Monday. Any questions before I sign off? Are there any questions before I sign off?
Not at the moment.
Right. You'll have questions when the code starts bombing, huh?
Can you upload this video of the lecture today?
Yes, I uploaded the Monday just before this class, and I will upload. Well, when I end the meeting, it takes about 40 minutes for Zoom to process and give me the. So I'll upload this afternoon.
Okay, thank you.
Mm-hmm.
And could you also share with us the presentation for surfaces?
Oh, so I haven't uploaded surfaces. Okay, so I'll upload surfaces and Lattice Boltzmann right now, right after I sign off.
Okay, thank you.
Mm-hmm. All right. We'll see you all on Monday. Enjoy the weather, however wildly changing it might be.
Okay, thank you.
Bye.